Okay, this lesson is on describing how we can describe the orientation of a coil in a magnetic field, and in particular when the direction of that coil changes. And we need to be able to deal with this when we're talking about generators. So in this diagram that I've got, what you see in front of you is a three-dimensional magnetic field. So this is like an isometric diagram, and this row of pink arrows represents the magnetic field going from left to right, and those lines are closest to us. Behind them there's another row of lines, 1, 2, 3, 4, 5. They're also magnetic field lines, but they're further back. And this row here is another row of magnetic field lines further back even still. This white rectangle represents a coil, and this coil is hinged on one edge, so it's able to move around like a door on a hinge. Now this is, like, as I said, like a three-dimensional isometric diagram. If we look straight down on this diagram in that direction, if we're looking down like that on the diagram, in other words a bird's eye view, then this is what we see. So looking down over there, we're going to view the situation like that. So this is row A of all the field lines, this is row B of the field lines further back, and this is row C further back still. So there's row A, there's row B, there's row C. So hopefully you can see this is a top version or a planned version of this diagram. Now we need to define a vector that describes the orientation of the area of a coil. In other words, we need to be able to draw in an arrow that tells us which way this coil or this loop is facing. And the way we define that vector is that it's simply at right angles to the face of the coil. So what I mean by the face, if you imagine this is the coil here, and we've shaded in the face of the coil. So if you imagine it was like, rather than a coil, like a piece of cardboard or a piece of sheet metal where it's all solid, then this would be the face of that. So if you can now imagine drawing a line which emerged from that at right angles to the surface, so that's a right angle there, to the surface of the coil, then that represents the normal to the coil. And so looking at this diagram over here, the normal to the coil, and I'll draw it in red or orange. The normal to the coil is off in that direction. So there's the normal to the coil. That's the same as that there. And that angle there at the moment is 90 degrees. Now, so I beg your pardon, I'll say that again. The angle between the normal and the plane of the coil is always 90 degrees. That's what's important. And I'll write that down. The angle between the face of the coil and the normal vector is always 90 degrees. So if we rotated the coil in the clockwise direction, according to this diagram, then our coil's moved around, it's spun around like a door on a hinge, and it's now oriented like this. And so the normal would be pointing in this direction. So as the coil moves, the normal to the coil moves. Now, and notice once again, that angle there is still 90 degrees between the coil and the normal. So it's always at 90 degrees to the face of the coil. Now in the next lesson, we're going to see how we can make use of this in actually describing the change in flux in a coil.